All right, welcome back. Another exciting installment of Bayesian psychometric methods. But this, at least, we're starting to get toward the finer points of things that still apply as we go forward. Last time, as you know, we covered most of the time was spent on the multidimensional aspect, which is challenging, not to say the least. But this time, we're going to talk about the remainder of the model fit aspect. Also, a little bit challenging, but I think it's something that it's not challenging in the sense that it's changed significantly from where I mentioned model fit methods in the earlier part of class. It's more challenging in the sense that it's a lot more information to have to understand to look at model fit. But before I begin, does anybody have any questions about what we covered last time or class or life? I wouldn't ask a life question. I'm probably not the guy to ask for that. But the rest of that, anything related to class, I think I might be able to answer. No questions. I like it. All right. What do you remember from last time? If you were sitting on the street and someone came up to you and said, "Can you help me with my PPMC?" Just sitting there, like in the park, and someone comes along. "Hey, do you know how to do PPMC? Could you help them?" Maybe. All right. Well, let's talk about it again. Remember, PPMC is for absolute model fit, and we sort of covered that the last time. But let's talk a little bit more about, I want to unpack a little bit more about what's happening because there's just so much in the model fit. So remember, in a psychometric model, as we look at our syntax here, this is an example model. This is the unidimensional model we fit to our data. The key is we're looking at model fit to our observed data. And in psychometric models, there's a lot of observed data, right? We have a bunch of, item responses usually nested within a person. So what we have to think about for model fit is model fit to characteristics of those item responses themselves. And the concept of model fit can be very, very complicated in a multidimensional model. Pardon me. When you have multiple outcomes, right? A multivariate model, and those outcomes aren't necessarily normally distributed. So back in CFA land, when everything was normally distributed, in non-Bayesian statistics, we have a whole set of model fit statistics, many of which rely upon the multivariate normal distribution that we believe underlies the data. But when we move away from multivariate normal distributions, we now are stuck in a world where what I like to call our target distribution, the distribution that we're trying to see that our data fit to, is no longer tractable. We can no longer create it. Meaning, for instance, what is a multivariate ordered logistic distribution? Or better yet, a multivariate multinomial distribution? Becomes very difficult to think about. In a sense, what we're looking for then is model fit to statistics of our data that can be somewhat understandable, but it may not fully understand full model fit. When I teach the multidimensional class next time, I go quite a bit into model fit methods for non-normal data, and I will cover that more. And in fact, if you want to see much more detail on that, there are slides on my website for it. But for now, just think of it this way. Our goal is once we create a bunch of these random data sets, right? Remember, we have 177 observations by people by 10 variables. So we're going to have this 177 by 10 data set for every iteration in our Markov chain, thanks to Stan's generated quantities that we have down here. What do we do with it? How do we summarize it? How do we determine model fit? Those are the questions that we have to ask with it. And what I'm going to teach you today is sort of a basic method, sort of looking at model fit to the correlation matrix, but know that you can modify that in multiple ways, and we sort of talked about that the last time too. All right, so let's take a look at this code one more time. I know we sort of ended the class right about here. The idea for model fit is in generated quantities, we have to go and start our PPMC process. So again, I'm going to repeat what I talked about the last time just to sort of make it clear again. SimY is a data set, right? SimY is where I'm going to put my 10 items, my 177 people's generated data. So sim y is going to be tracked throughout the chain itself. And here, um, to do that, to generate data for each item and observation, I build this loop, looping over items and observations, and I use the random number generator associated with the ordered logistics statistic. Pardon me. The input to this random number generator is the same input that you have on your model statement, right? And that just ensures that at each step of the chain, the lambdas, thetas, and thresholds at that current iteration are used to generate data in this random number generator. One of the nice things about Stan is for every distribution that you have, ordered logistic, there will be a random number generator that comes with it as well too. At least for the distributions that I've used. I haven't yet reached one that hasn't been there, but in the true sense of philosophy of science, I haven't looked at all of them. It's hard to prove a null without going exhaustively, and I don't have the time to be exhaustive. So let's put it this way. For all the distributions that I'm familiar with, there's a random number generator. That makes it easy. That's the easy part, thankfully. Right? So Stan will do the do the hard part for us in generating data. Now, afterwards, the problem is in October, I showed you methods where Stan will compute the PPMC as well too, sort of your posterior predictive p-value. Remember the probability that your observed statistic is below where or basically what percentile is your observed statistic at in your predictive distribution of the statistic. We could do that in Stan here, but the problem is we have so many different correlations and so many different statistics to come out with. Remember, with 10 items, each item has a mean, a standard deviation potentially. Each item may have, or each pair of items may have a correlation we have to look at. There's just a lot to look at. So what I end up doing usually once I get into psychometric models is I let Stan do the simulation for me to generate the simulated data sets. But then outside of Stan, I build the code to parse that and to build it into something where I evaluate model fit. Does that make sense? Questions about the process or anything, thoughts about that? Eh, okay. Um, so here you can see on my slides for one theta, the only difference between one theta and two thetas in this process, just to sort of I get your idea about what model fit is our call to our ordered logistic, right? For one theta, there's our lambda, there's our theta, that's our unidimensional model that we've used most of the class. And then alternatively, if we want to compare that with a two-parameter or two-dimensional theta model, then the model changes to be what the model input happened to be for the multidimensional model. So in terms of model fit, if you're thinking about the models that you're running, this generic code, this code's very generic. It would apply for most places. The only catch would be you just have to re-specify your model in the middle of the code to build it. Okay? Okay. Well, let's process this toward the end here. This is really where I wanted to set things up. Excuse me for coughing. Got a lot of that these days. Let's see here. Setting up the PPMC. So what I'm doing over here, really wanted to talk a little bit more about um, how the data look when they come out of Stan. So sim data is me taking my Stan model object and taking the draws for every variable that starts with sim y. Now remember, sim y was the variable I created to store my simulated data sets in Stan, right? So here, me selecting sim y gives me sim data. The column names of sim data look like this, right? So this is probably a bad idea. We'll see how this works. Come on, you can do it. Come on. There it is. That's my sim data object. It's slowly coming in. Remember, it's massive, right? There's 3.5, wait, hold on, 35 million observations here. 35 million data points from a simple two parameter or simple, unidimensional model here. It's a lot. But take a look at what happens here. Remember, each possible element of those 177 values, right? The 177 person by 10, actually 1,700 values is listed here. Right? So SimY11 represents the very first person's first variable's score that was simulated, right? And so this row 1 here, represents the simulation for the first iteration. So it's massive, right? There's 1,770 total columns, right? So that all that row contains is the first data set. So it's our job to take that row, put it into a data set, and then build statistics out of it. And that's the process that we're going through here. Okay? Am I going too quickly? Too slow? All right. So again, very big data. So what I ended up doing is creating a list of names, right? These are the pairs of correlations. So what I'm going to build is PPMC for two quantities. One is each item's mean, right? So there'll be 10 different means, and one is for each pair of items correlation. And I'm going to use the Pearson correlation in this case. You could use a tetrachoric or polychoric. I mentioned that in my slides last time. The tetrachoric and polychoric have a few other catches that cause a few problems. One being that in small data sets, if you have 0 people in one contingency table, a pair of items, it will not return a result that's valid. So I'm saying with Pearson for this example, but just note that more probably better measures are out there. It just takes a lot more detail to implement them. Um, so here, I'm going to create a samples object to store the correlation and the mean. And so what this object is going to do, this PPMC samples correlation, is going to be a data frame where each simulated correlation is saved. Right. So what do I mean by that? Remember, in this in my big data frame, which was sim data right here, that huge data matrix, I'm not even going to open it up again because it's so big. That first row turned out to be 177 by 10 data matrix. So from that first row, I'm going to get 10 means and 45 correlations, right? 10 choose 2 correlations. So if you think about it, each row of the sim data, I can still calculate 10 means and 45 correlations from. So that's what I'm going to save in correlation and mean right here. Okay? Okay. So I set the sample to 1, you're going to see this process play itself out. I'm creating a sample data frame that's just going to hold my data. And then for each item, let me show you what happens. If I set an item, the first item here, what I'm looking for, this grep function, searches a set of character strings for a pattern. It's a very helpful function. If you're into text processing in R, learn grep. Grep is the thing. If you're into text processing anywhere, it's old, very old. Grep is like a Unix function way back when, but it's awesome. So I'm searching for SimY involving this item. What am I talking about here? This is the search that I'm looking for. Anything that's SimY. Now, I'm sorry that you can't see very well down here, but this SimY part, that thing right there, the double slashes mean that tell R that there's a special character. That's the bracket. That's a special character, so it has to be denoted with slashes. So the way that you'd read this is SimY bracket 1, and then the double slashes here have a comma, right? And the reason for that, again, is because I'm looking for every one of these column names that have a 1 in it, right? So here, I grab the columns that have item 1. These are all the columns, right? And then I take those columns of data, right? This is my sim data for those columns right here, and I create a data matrix with it for that first item. I added it to sample data. So right there are all the observations for item 1 for the 177 people we have. Okay? So if I run this loop all the way over for all the items, you'll note that sample data now is full. This sample data right here, that's called sample data, it's simulated, right? This is a simulated data set. So this is what we're going to use to summarize. First thing we need is the mean. And in this simulated data, those are our item means. Oops, right here. Not bad, right? And then the same thing happens. We could go and grab the correlation matrix. So here are our correlation matrix between the items in our simulated data. And from there, we grab our correlation. So that process is one iteration of our output from Stan, right? One value of this, the posterior. So if I run this over all the rows of sim data, right, for all of our posterior samples, now I'm going to come up with a lot of correlations, a distribution for each correlation, a distribution for each item mean, and I just need my zoom window to cooperate a little bit here. Let me move this to where I can see it better. That little annotate button is in my way and I can't move it. Well, I'll outsmart Zoom though, all right? The Zoom overlords won't stop me. As this is running, do you have any questions about this? Is this helpful in thinking about what's happening? I'm going overboard on this because honestly, like it may sound like building the Bayes model is the hard part, but once you're used to building the Bayes model, the hardest part is actually checking the model fit. There's all sorts of hard parts, but everybody who does Bayes does so because they like challenges, right? Sure, sure thing. All right, in the absence of questions, I'll just scoot up a little bit here. That's the processing step I just talked about. There we go. Now we have everything here. What I do afterwards is I add the pair names to each of my samples, correlations, and the means. And this is where we can tabulate some of our results right here. For instance, or we can take a look at it. This right here is the sample distribution of our first item's mean, right? So what do we have? This is telling us what? This is what we call a predictive distribution, right? Once we did all of our simulated data sets, this is the mean of item one across all of our simulated data sets. So it has this nice shape to it. Nice. It looks like a nice distribution, doesn't it? I don't know. Can't believe I asked that question, to be honest with you. I'm sitting here thinking, did I really just ask that? I really did. Okay. So the red line is where our observed mean for item one happens to fall. So would you say that the first, does our model fit the item one mean well? What do you think? Why would you say, I see a from those of you on the camera on, it sounds like, yeah, kind of. I agree. Yeah, kind of. Here's why, right? The mean of our item that we observed happens to be in the middle of the distribution of the predictive distribution, right? And what the predictive distribution represents is where our model thinks that mean should be, right? So if our item's mean is right in the middle of where the model thinks the item should be, yeah, that sounds like good fit, right? The only time this would be a problem is if our item mean were somewhere way beyond where our model thought the mean should be, right? Remember, predictive distribution is another way of saying this is what the model thinks our data look like. Okay? The red dashed line is what our data actually look like. Now, the same thing can happen with a correlation. And actually, to me, in psychometric models, correlation is usually the most interesting statistic, some bivariate statistic. Here, we have our posterior predictive distribution. This is the Pearson correlation between item one and item two. You can see our model thinks it's somewhere most likely between 0.5 and 0.6. Our red dashed line is our Pearson observed correlation between item one and item two. And again, it's in the middle of the predictive distribution. So this is a nice sign for us. It means our data and our model working out okay. Look like it fit, at least for this one statistic and this one item. So does that mean it fits overall? Can we just be done? No, of course not. We got all these items. We got all these statistics. So what do we do instead? This is where the next section of my syntax comes from. if you're following along with the slides, slide 14 here, this is me trying to build a way of looking at these results more quickly than eyeballing every single graph I have. And so what I'm going to do is I'm going to loop through every item and create some summary statistics for each posterior distribution, in addition to some summary statistics for where our observed mean happens to fall and how different the two happen to look. Okay? So specifically what I'm going to do, this mean summary, if I is where I'm going to save it. If I initialize to the first item, what you're going to see is first of all, right here, is this first item, PPMC samples mean. This is all of the means from all of our simulated data sets. Anyone ever seen the eCDF function before? And it's called an empirical CDF. A CDF. What's a CDF? Cumulative distribution function, right? You can think of this as the function that tells you where what the probability of being at or below a value happens to be in a distribution. The E stands for empirical, meaning it's trying to form a cumulative distribution based on all the data we give it, in this case, in the mean. So if I take temp dist and I give it the value of 2, let's say how many means are below 2? It would tell us none are. If I ask it 10 temp dist and what proportion of means are below 3, it'd say all of them are 100%. If I put some value in the middle here, like 2.4, that would tell us that some 70% of the distribution is below 2.4 for these sample means. That's what it's telling us. And so why we use the eCDF is it gives us the posterior predictive p-value. Right? What we want to know is what number or what proportion of posterior predictive sample means. Go back to the plot here. Nope, not that way. This plot over here, this plot. What we want to know is the proportion of this curve that's below the red dashed line. That's what eCDF tells us. It's kind of a cool base R function. Back in the old days of R, that blew my mind. Hey, yeah, that was awesome. All right. The PPMC mean gives us the mean of just that overall, right? So this is our overall average of all the simulated means, 2.35. Our observed mean is our overall average in our data, 2.36. That's pretty cool. So we should probably do something to compare the two, and that's exactly what I do next. In this data frame, I'm saving the mean of the PPMC draws, the observed mean, the difference between observed and PPMC mean, and then this PCT, which is simply the posterior predictive p-value, the number of predictive means below our observed mean. So once I run that, you'll see we have a table here. Whoops. This table gives us these details for each of our means, right? And you can take a look here. What I go to first, if I want to talk about which mean is in a tail, I can look at this PCT column, because if this number is super tiny, it means the red dashed line would be over in this tail, the left tail. And if that number is super big, very close to 1, it means the red dashed line would be in the upper tail. So this is very much like looking at basic statistics. What percentile are you at for our observed mean? And we can see that most of our means are right in the middle of the distribution, right? The smallest percentile is 0.37. The biggest is like 0.58, 587, somewhere around there. So pretty good shape. Looks like things tend to fit the mean, but that's expected, actually. We should fit the mean, right? How we doing? Concept okay? Let's do that same concept, but for correlations, right? So again, here we're going to do the same process of tabulating. We're going to calculate our observed correlation, right? The average. Pardon me. We're going to talk about our average of PPMC correlations, right? Our simulated data correlation. We're going to talk about our observed correlation. We'll talk about the difference between the two. We'll give that posterior predictive p-value. And I'm actually going to add one other flag to this, which is whether or not this PCT value, posterior predictive p-value, is in the lower 2.5% of the distribution or in the upper 2.5%. I'm making those arbitrary distinctions, but that's sort of my thought is that whether or not we are close, what our model thinks the correlation should be is close to where our observed data should be. Now, the only other difference here is that instead of having 10 means, I have 45 correlations. So it's a lot more complicated of a step. And so what I get here is the following. These are our observed pairs of correlations. You can see the difference. This is our distribution of residuals, right? So for instance, item 1 and item 10 has a very large residual, not large and negative, I guess. Very residual in absolute terms away from 0 is bad. But you can see if I sort by residual, these are the worst items. There are 4 items that tend to have correlations in the tails, right? 1 and 10, 3 and 9, and so forth. And if I get bold, see if I can do this. Nah, I don't know that I can. Never mind. I won't. I can't really plot it very well. But this is then, oh boy. These are our correlations that you see here. Right. So the question I have for you in PPMC is this good or is it bad? Does our model fit our data absolutely or does it not? What do you think? Yeah, who knows, right? And that's part of the problem with PPMC. Um, this core summary, we have 4 correlations that I would say are not in the middle of the distribution. I don't know what we would normally observe if we generated data from the true model. Would we observe any? I don't know. I don't have a reference for this statistic. I can only describe it in certain terms. But what I like to do there is I actually like to think about the following, right? So here, in terms of what I like to do is for each item, count up how many other items it is it is paired with that don't have a good correlation fit. Does that make sense? All right. So for instance, take a look at my table. Item 1 and 10, there's that correlation was flagged as being in the tail, right? Our model thought our correlation should be 0.413. Our observed correlation was actually 256. So we overestimated the correlation there. So item 1 and item 10 were involved in that. But then if you go 2 steps down, you see item 1 and item 3 show up in this as well, where 0.493 happens to be what our model thinks the correlation is, and 0.347 is what the correlation was in our data. So what you're seeing here to me is, wait a minute, item 1 shows up with both of these. So what I would like to do is tabulate and say, hey, item 1 is in 2 bad pairs of correlations. That's what I've done over here in this bad items that you see over here. Similarly, item 10 shows up in one, item 3 shows up in another. And actually on this one, evidently my simulation and what you see here uh, also include item 7 and item 4, which you don't actually see on my slides, and that's a difference between random numbers. 4 and 7 don't fit in this one very well. So actually, no, this is all item 1, item 3. This is all the univariate model right here. This is right here. That's our bad items for the univariate model. Right? So if you are using absolute fit, you could calculate how many bad items you have. You could also come up with a network. I showed this before. I feel like I showed this before of, I guess I can't zoom in anymore. Well, this is the closest I can get. This network 3D package tries to tell you which items tend to be bad with each other. And what I'm doing with this is thinking about remedies for model fit, right? So when you have a misfitting pair of items, what does that mean in data? usually means that something's wrong with our model. Now, it could be our model specification, it could be our Q matrix, right? So when we ran one theta, we have all these model fit values for our bad items, right? We have four pairs that were not quite good. Our core summary had, well, I lost it, but it was on the thing I had on the screen there was our four values. What do you do to let's imagine that you were you thought that this indicated that you it was good fit but not quite good enough. What would you do about it? How would you fix it? Good luck, right? Um, in frequentist world, sometimes you might look at statistics like modification indices, although a lot of people don't like doing that. I think that's data snooping. I don't disagree. I mean, you sort of have to do that. Do what you got to do. The other thing you can do, though, there's sort of two remedies to model fit. One is change your model. In this case, change your Q matrix, right? So if you had one theta, maybe you need two, right? The other remedy happens to be drop items that don't fit well, right? So if we saw item one not fitting well with all the rest, we might remove item one altogether from the analysis and rerun the whole work. Let's think about the ramifications for both of those, right? Changing the Q matrix, what does that mean? That means saying, acknowledging that, hey, this model fit really indicates that there may be more latent variables involved in my data than I think. So I need to go and try to estimate or come up with a better set of data variables, right? Dropping an item, not the most elegant solution, but it's possible, right? In fact, I would say in most of the shops I've actually done live practical work with dropping items is routine, but there are some ramifications for dropping items. One being um, the validity of your instrument. Each item is a contributor to validity, right? The content validity of your instrument. Um, but I would say that if an item doesn't fit, that also threatens the validity of your instrument as well too. So, so the two remedies I look at here is change the Q matrix, drop items. I guess you could change the model. I guess we could get a more complicated model, like a nominal response or create a partial credit model would also be a little another example here. How are we doing? Question wise. And again, my eyes are pointed this way because my setup has changed a little bit again. But anybody right here? Is this you understand the process? Excellent. Vladimir. Right. Correct. What absolute fit happens to be? What's the standard for absolute fit? We don't have good standards for that in Bayesian statistics. You know, in frequentist in non-Bayesian statistics, if you were in SEM world, there's a bunch of standards for model fit. Now, nobody likes those standards, and in fact, in recent years, those standards have been under investigation. What am I talking about? If I take an RMSEA, from a confirmatory factor analysis, I know that I want that to be less than 0.05 by a paper called Hu and Bentler from 1999. They said, well, 0.08 is probably okay. And then in recent years, people have evaluated saying, well, actually, it's a lot more nuanced than that. It depends on a lot of different other factors, how well your measurement is, how many items you have, how many people you have, et cetera, et cetera. We in Bayes statistics don't have a 0.05, don't have a 0.08, right? Um, so for me, I don't know what good enough fit happens to be. But I do know that describing the model fit in the full detail is the best way forward. So even though you're like, hey, my model, what basically what I'm saying is if you're writing a paper and you're using Bayesian statistics, rather than saying, hey, RMSEA is less than 0.08, model fit's good, which these days may not even work for review, um, I would basically say, hey, I had four values that were outside in my posterior predictive check, 4 out of 45 correlations, something along those lines that would describe it better. And that would provide a much more rich detail, I think. Now, there are model fit methods. Again, I mentioned one of our former students has done a couple different methods to try to look at like an overall posterior predictive model check for a single number. So, for instance, like in categorical data, there's a model fit index called M2. Again, in my multivariate class, you'd learn about multidimensional class, you'd learn about that. Um, we can come up with a version of posterior predictive check for model 2, M2 as well, sort of a comparison. But that's sort of I haven't implemented it here. It's a little bit harder to do. Probably need a package to be able to do that. But generally speaking, uh, not good guidelines, I would say that. But in some ways, not good guidelines, but a whole lot of detail as to where model fit is not happening for your model. So that's the comparison. Does that help? Transparency is important, but let's be real. This is transparency taken to an extreme, right? Where every single possible way of looking at data are there. Heck, I created a mean for each item, and I created a correlation for each item, and I compared those. I could have gone further. I could have been like, hey, what about three-way tables? Could I come up with a contingency table for three-way tables, like x1, x2, x3, or better yet, y1, y2, y3, right? How well do I fit three-way tables or four-way tables? There's all sorts of ways you can do it. But yes, it's overwhelming, but it's very detailed. And I like that about it. Other questions? A point here, but I'll look over here. No, no other questions. All right. So we get into relative model fit then. All right. Actually, let me give one last bit of color. Uh, Here is the other thing I wanted to talk about. In um, in our model, for one dimension, you see this set of model fit problems, right? So item one showed up on two flag correlations, item three, and so forth. When we had a multidimensional model, that number came down just a bit, right? So basically, the difference between one theta and two thetas. In one theta, this was with a set of bad items, but this corresponded to four correlations that were flagged. When we add that second theta and a correlation between the two, we went from four items that were flagged down to two. So in some ways, we got better model fit. That's great. That's what we want. But what we don't know is that too much, right? There's no penalty for it. In posterior predictive model check, it's model fit absolute without regard to how many parameters are in your model or in your data. So what we don't know, we can say that we had two fewer correlations that were bad out of the 45 when we added the second theta. But what we don't know is whether or not that actually means that second theta fits better in a relative sense. Beyond that, we also know from last time that theta's correlation was quite high, right? It was like 0.99, right? The correlation between the two thetas. So it didn't really seem like we had a second theta, even though we got better model fit from it. So that's one of the features of model fit. When it comes to absolute model fit, there's no penalty for complexity of the model. Right? So there's nothing that would stop you from adding and adding and adding and adding to get great model fit. But there's pitfalls to adding to your model, right? You lose generalizability. You've sort of already done data snooping, right? It may not apply beyond what you've done, very well. It may be sample specific. So we need something else to sort of help us understand whether or not two thetas, this model fit improvement, is really a significant improvement in terms of what we understand from the model. And that's where relative model fit comes in. Remember, relative model fit from before, we had two categories. There were they fall under a broad class of ideas called information criteria. Um, WAIC, Watanabe Akaiike information criterion. or widely available information criterion. People use both words for the acronym. And then leave one out as implemented with Pareto smooth importance sampling, or LOO-PSIS. Can't even say that. We can use both of those to compare the fit of the two Bayesian models. I will note there's some really interesting philosophical considerations to think about here. One is that if you look at what we're doing in Bayes versus what we do in non-Bayes, if we're using maximum likelihood for this model right here, not CFA, but in categorical data, we use something called marginal maximum likelihood, right? Usually implemented with an EM algorithm or something along those lines, close to, or some combination of algorithms. But marginal refers to removing the latent variables from the likelihood function itself. And we have to do that from a statistical point of view to ensure that our estimates are consistent, meaning as n goes to infinity, they converge to their true values with probability 1. Okay? Marginalizing, though, is also what happens when we look at model fit, for instance, in M2 or in other model fit statistics. Now, our method in Bayes does not marginalize. We, for every step of the chain, are sampling theta. So many of our model fit statistics are based on something we call a conditional model, a conditional log likelihood for every step. And to me, there's some debate over what to use, right? There are some classes of models, and this is one of them, we could have coded Stan a little bit differently and done a marginalized Bayesian estimation method, right? What do I mean by that? In this, we could have created our own likelihood function and used some type of numeric integration to integrate across the thetas that we have in Stan in every step of the chain. And you're thinking, why would we do that? Correct. But if you really want that marginal likelihood, that's where you could build it. But the point I'm trying to make is that is a marginalized version, whereas what we have here is something like a conditional version. And the likelihoods themselves are not directly comparable between marginal and conditional. So what I'm going to show you is this based on conditional likelihoods using WAIC and leave one out to look at model fit. But I'm going to tell you that in my head, I go back and forth on this quite often, whether this is a good way, whether it's an accurate way or not. I need to do a little bit more reading, maybe do a little study. Anybody's interested in research topics, this is an interesting topic, but maybe for me, yeah, for you, but we'll see. Trying to convince you it's an interesting topic. So let's talk about how we implement this. What we have to calculate for each of leave one out and WAIC, these run on something called the expected log posterior density, right? That is basically the log likelihood of your observed data for each person and item, conditional on what your model thinks that person's distribution should look like. So let's kind of parse this down. Remember, in our model, we have ordered logistic right over here. And actually, let's go up to the univariate model, since that's what I have on my screen here. So we have our ordered logistic function for our univariate greater response model. To calculate WAIC, I need to come up with, for every person, this person likelihood, which is the expected log posterior density in Stan. And how I do that is basically I have to sum across the likelihood for each person of all the items, right? So let me walk through the process. Our model, for every given iteration, we have a lambda for that item, we have a theta for that person, and we have a set of thresholds for that item. With these values, Stan creates a multinomial distribution, right? A categorical distribution. That person has a probability of answering 1, 2, 3, 4, or 5, right? The ordered logistic LPMF then takes that probability, looks at the response the person actually provided, right? Let's say it was a 2, and takes the log probability of that response and adds it to the person likelihood. So what it's doing at every step of the chain is calculating how likely it is, based on our model, that we observe the data that person gave us. That's what this person log likelihood is doing. So we calculate that over and over and over. And at the end of all of that calculation, we can use Stan's built-in functions or the LOO's built-in functions to calculate information criteria. So from a conceptual point of view, what we're doing here is quite complicated. The math behind it is probably beyond me. But from a practical point of view, what do we have to do is actually more simple than PPMC. We need to save a person log likelihood so that for every iteration of our Markov chain, we can talk about how likely that person's vector of data happened to be given our model parameters. Okay? It's like a person fit statistic. So we can calculate both of those. And then, so literally, again, the other part I wanted to note here was that the function ordered logistic is our model. Well, it turns out every model that I know of, again, not proving a null, but for every model I know of in Stan, there's an LPMF that goes as well with it. So not only do you get, when you put a model statement in, you can do PPMC with it, but you can also do person likelihood with it as well. That makes life, let me tell you, this makes life a lot easier than otherwise. Okay? You may not believe it, but I promise. I feel like I'm here telling you all this stuff, and you're like, why the hell would I ever do Bayes? Because you'll be part of a club that you will never ever leave. Never mind. Never walk alone. No, there's a lot of benefits to Bayes, particularly if you have lots and lots of data or lots and lots of latent variables. All right, but once you do all that, there's a WAIC function that you can actually put these in. And WAIC, if I can get down to where that happens to be in my code. So everything you see above where I'm at on my line on my screen was PPMC. To do relative model fit, here's your lines of code afterwards, right here. What do you like better, PPMC? No, it's a lot simpler this way, right? All right. WAIC tells us what? This is for our unidimensional model. These are numbers that are calculated based on our expected log posterior density. That is just telling us the WAIC for the unidimensional. Here's the WAIC for the multidimensional. And what we do in comparing WAIC is we look for the smaller number of WAIC, right? So here, our estimate of WAIC for unidimensional is 2965.6 with a standard error of 140.8. And for our multidimensional, it's 2983.2 with a standard error of 136.1. So by the estimate, because the unidimensional is smaller, we would favor unidimensional. However, and this is one of the cool things in Bayes, we can see how much uncertainty we have around that estimate. And I would tell you that the difference is what, about 18, about, if we take the two-dimensional minus the one-dimensional, it's about 18 points away. But our standard errors are both in the 140s and 130s. So most likely, that's within range to say we're not sure which one fits better. Or better yet, they fit about equally well, which makes sense, right? Especially for comparing a two-dimensional model that's about to collapse into a unidimensional model, because that correlation becomes one. All right. Now, that's the funny part. You might be noticed on here that 173 estimates are greater than 0.4. We recommend trying LOO, L-O-O. So should we try LOO? Sure. This is our LOO, or leave one out, for the unidimensional model. And this tells us how whether or not our sampling is good or bad. And you'll note that it didn't. Stan didn't like our WAIC, but it really doesn't like our LOO either. 151 samples or K values are in the bad range, right? Some values are too high. Now you can go get help for details, but good luck with that. What do you do? I don't know. And same thing here for the two-dimensional. The LOO package that comes with or that's part of the stand suite of options will compare the two numbers. It'll come up with a difference. And basically here it says the two-dimensional is slightly better. It's smaller than unidimensional with respect to leave one out. A difference of negative 2.5, but the standard error, the difference is 5. And these values are somewhat suspect as well, too. So what I'm getting from this is, again, model fit, they're roughly fit the same, is what it's telling us, right? So what would you do in this situation? Which model fits better? Which one would you prefer? How many of you say unidimensional? See eyebrows? Really, really responsive group today. I like it. All right, that was how I was as a student. No big deal. Nope, not throwing stones from my student house. How many of you would say the two-dimensional model? Anybody? Nobody. So here, let me give you my logic. I would pick the unidimensional model also. And the reason for it is that when you have a Q matrix where each item only measures one factor, one trait, right? Then if those traits are correlated with a value of one, you don't have a two-dimensional model, you have a one-dimensional model. And I think that's what we're seeing here, right? Our two-dimensional model is so close to unidimensional that we can't tell which one fits better because they're effectively the same model, right? So in that case, I wouldn't pick the two-dimensional model because that correlation is so high at 0.99 that there really isn't two dimensions. There's just one. So the what I'm gathering here is I used Bayesian methods to provide evidence for where fit happens to be, but then I got to use logic to figure out the final bit of it, right? Our Bayesian method said, I don't know which one fits better. They're about the same. But logic would say one is nested in the other. So I should take the simpler model, in this case, the unidimensional model, to describe things. How's that sound? Anybody disagree with that logic or reasoning? It's okay. Believe me, everybody disagrees with me. Some days it feels like it's nothing but disagreement. So I'm ready. I can handle it. And I won't take it personally. Okay. Questions on anything about model fit? Yes. 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 Yeah. Yes. Technically speaking, when it comes to anything with information criteria, yes. So model comparisons, LOO or WAIC, yes. When it comes to posterior predictive model checks, because they're not penalized by amount of data or anything else, they can still be the same because they're just summarizing what you do observe. But yes, we are going to talk about the next lecture is ready to go. We'll be pulling that up in just a moment, model fit. But generally speaking, you'll want to have the same observations in your data to ensure model comparisons as well too. And actually, even for posterior for predictive model checks, it makes more sense to leave it that way, but it's not a technical requirement. From a philosophical standpoint, from a good practice standpoint, yeah, probably want to be the same. But um, from a statistical standpoint, it's not relying on. We're not calculating anything other than just summary statistics, so it still should function. That help? That work? Great. Other questions? No questions. Moving on then. So that's it. Ta-da! I think there's some cool stuff you could come up with in Bayesian model fit, particularly looking at some of the dynamic model fit indices that are out there these days, work that's coming out. So if anybody's looking for a topic for quant method research, here's a good one. All right, let's stop. I'm going to stop one recording and start another one. This is dangerous. All right.